Okay, these are test 2 solutions, and we were given a function. We were asked to find the tangent line, the equation of the tangent line to the point 0, 9, and also the normal line at that same point. So we differentiate the function 4x to the third plus 9e to the x. We plugged in 0 for the point to find the slope at that point, slope of the tangent line to the graph of the function at that point, and we get 9. Y minus y1, the point slope form, equals the slope times x minus x1, and we plugged in the numbers 9 for y1 and 0 for x1 and 9 for the slope, and we get this. Moving to the other side, this is the tangent. Now the normal line will be perpendicular to the tangent line, so if this is the tangent line to the graph, this will be the normal line, tangent, normal. So two lines that are perpendicular have multiplicative inverses, negative multiplicative inverses of each other's slopes. So in this case, if the slope of one is 9, the other one will be negative 1 over 9. And the whole thing holds, everything is the same except the slope. Here we were asked to graph the function. First we find its domain. It's a piecewise defined function. We find its domain from negative infinity to 2, including 2, and from 2 to infinity. So this symbolizes the bracket, negative infinity to 2, and then 2 to infinity with the parenthesis. So between negative infinity and 2, I used 2 minus x. Between 2 and infinity, I used x minus 2 squared, because it's the same with x squared minus 4x plus 4. So this is the same with x squared minus 4x plus 4. I plugged in numbers, 0, and then I got 2, and then 2 and I got 0. I plugged in 2 here and I got 0. I plugged in 3 and I got 1. So I see the domain is this. When I graph the function, I'll find the range in a moment. So I have the points. This is a linear function. This is quadratic. Obviously the range is from 0 to infinity. I find the derivative to be negative 1 and 2x minus 4 for the second branch, 2x minus 4. I cannot include the equal symbol anywhere because the limit from the left of this number is negative 1 and the limit from the right of this function, right of 2, is 0. They are not the same. Because they're not the same, the function is differentiable everywhere except at x equals 2 where it has a corner. Then we were asked to differentiate this function. So the top function prime is 1 times t minus 1 squared plus minus t plus 4, and differentiate this as 2t minus 1 times the inner function prime, which is 1, divided by the numerator squared. I will factor out t minus 1, and then I get t minus 1 minus 2t minus 8. So we get t minus 1 simplified, 1 factor, and the numerator has negative t, and then negative t, and then minus 9. Factor out negative 1, this is the final form. Here, 7 minus secant squared over tangent x, negative secant the top prime. It's negative secant tangent times tangent, because secant prime is secant tangent, but there is a minus in front that I have to keep, and 7 prime is 0. And secant tangent times tangent is this, minus 7 minus secant tangent times the denominator prime, which is secant squared, over the denominator squared. Don't try anything else, this is good enough. Here y equals cotangent squared sine theta. Y prime will be 2 times cotangent sine theta times cotangent prime, which is negative cosecant squared of the argument, times the inner function prime, which is cosine. There is nothing else we can do here. Yes, so we can put minus in front, but that's good enough. Y equals natural log of x plus the square root of x squared minus 9. Natural log prime is 1 over this, times the inner function prime, which is 1, plus 1 over 2 the square root of x squared minus 9 times the inner function prime, which is 2x, and I will simplify it 2. I find the least common denominator here to be the square root of x squared minus 9, and I have to multiply 1 by the square root of x squared minus 9. That's how I get in the numerator x plus the square root of x squared minus 9, which happens to simplify with the denominator. So the final, simplified form is this. Here we don't have any formula to apply. We have to use a logarithmic differentiation. We apply log to both sides. I meant no differentiation rule to apply. We apply natural log to both sides. 9 over x comes in front, using the power rule of the log, times natural log of tangent. Now we differentiate implicitly. 1 over y times dy over dx equals 9 stays outside. 1 over x prime, if we remember, 1 over negative 1 over x squared, times natural log plus 1 over x times natural log prime, which is 1 over tangent times the inner function prime. And I multiply by y in the form of tangent x raised to 9 over x, and the rest gets copied. Here, we're asked to differentiate this function. It's 1 over, so arctangent prime is 1 over 1 plus the argument squared, times the inner function prime, which is cosine 5x, times the further inner function prime, which is 5. And now hyperbolic tangent squared is hyperbolic secant squared of 3x cubed times 9x squared. And then I just condense it a little bit with 5 cosine and plus 9x squared secant squared. Y equals this, prime, 1 over 2, the square root of that, times the inner function prime, which is 8, times e to 9x, times the inner function prime, which is 9. I will simplify, and I get 4 times 9, which is 36, e to 9x over the square root. Here we're asked to find the second derivative of this function. I have to apply the product rule a couple of times. So 5x to the 4th e to the x plus x to the 5th e to the x. I factor out x to the 4th e to the x, and I get 5 plus x. Really no need, because I'm not going to do anything with this. The second derivative will be 20x cubed e to the x plus 5x to the 4th e to the x plus 5x to the 4th e to the x plus 5 to the x to the 5th times e to the x. So these two are like terms, and I combine them here. And I factor out x to the 3rd e to the x, and I get this in parentheses. The limit, I use L'Hopital's rule because it's 0 over 0. When I differentiate the top, I have cosine of 9x times the inner function prime, which is 9 over 1. So when I plug in 0, I get 9. And here, again, it's 0 over 0. When I differentiate using L'Hopital's rule, the denominator is 4 cosine 4x. The numerator is negative sine 3x with 3 multiplied by 3. This goes to 0, this goes to 1. The answer is 0. Implicit differentiation, dy over dx times cosine x. Sine prime is negative, cosine prime is negative sine times y equals 6x plus 4y dy over dx. These two have to be on one side, these two have to be on one side. When I move this here, it becomes negative, and I factor out dy over dx. And here I have the 6x plus y sine x, and I divide this by this to get dy over dx. To approximate sine 89, I use the approximation f of x plus f prime of x dx. And where the function is sine x, x is 90 degrees, and dx is negative 1 degree, has to be changed into radians. I didn't even have to write radians here, because it's pi. Once it's pi, we know it's radians. So f prime of x is cosine x, and all we do is just put f of x plus f prime of x times negative 1 degree times pi over 180. So it happens that since cosine of 90 is 0, all this term is 0, so it's approximately 1. Here we were asked to find the rate of change of the area, knowing the rate of change of the length and the width of a rectangle. So these were given to us. We were also told when y is 12 and x is 15 centimeters. So I implicit differentiate. There are three functions of time: a, the area; x, the length; y, the width. So this is d over dt, and this is the product rule: dx over dt times y plus x times dy over dt. I have all the numbers, I plug them in. 1 times 12 plus 5 times 15 times 9, I get this. Careful with the measurement unit, centimeters squared per second. Here we're given a cost function. We're asked to find the marginal cost. I just differentiated 2 plus 0.06x plus 0.0009x squared. I was asked to find C prime of 120. I plugged it in. I got 22.16. I was asked to find. We were asked to find the exact difference in the cost of producing the 121st item. 121. Cost of 121 units minus cost of 120 units. I plugged them in and I got this. And now we were also asked to approximate using differentials the cost of 121. Well, it's 121, which is x plus 1. It's the cost of 120 plus the cost prime, marginal cost of 120 times 1. So I copied this from here for C of 120. And C prime of 120 multiplied by 1 is this, right here from part B. So that's the approximate cost for producing the 121st item, this one. And I just showed that these are very close. And finally, the extra credit, we were asked to find where the tangent is at the point where the tangent is horizontal. I differentiate 2 natural log 2 minus 1 divided by the inner function prime times the inner function prime, which is 1. So y prime equals 0. A fraction is 0 only when the numerator is 0. So natural log of x plus 2, of course, 2 is the constant. So we change this into an exponential equation. E raised to 0 equals x plus 4. But e to 0 is 1. So 1 minus 4 will be negative 3. I have to plug in back in the function and show and find the point where the tangent is horizontal. And I got that point negative 3, comma 0. When you plug in negative 3 in the original function, you get 1. Natural log 1 is 0. 0 squared is 0. Thank you.